enhancement of seismic performance of civil structures, some of the recent activities at Structural Engineering Lab, IIT Guwahati. So before I go to the speaker, let me just brief about Ramco Cements as such and the initiatives that we have been taking in the recent past. Of course, all the professionals are well aware of Ramco Cements because we have been doing a lot of initiatives, and in the recent past, we have also been organizing a number of webinars so that there could be what you call this sharing of knowledge. Just a brief of the company. Ramco Cements, apart from manufacturing cement, also produces ready-mix concrete, dry mortar products, and operates one of the largest wind farms in the country. It generates on an average of 2,400 lakh units per annum from wind energy only. And the latest technology is incorporated in all stages of manufacturing, starting from mining till packing. And you would see surface miners, you could see vertical roller mills, and you could see various other initiatives which has been started over the years since Ramco Cements entered the cement industry since the 1960s. And of course, we took a lot of initiatives in promoting blended cement because of the qualitative aspects. Of course, environmental benefits are also there, but apart from that, qualitative aspects like low heat of hydration, durability perspective, and we have also taken a number of steps for using energy efficiently. So, because of which we have been receiving a number of awards. So, sustainability has been of great importance in the operations of the company. And we have won several awards in this regard. And of course, in the area of corporate social responsibility, also we have taken a number of initiatives. The first cement manufacturer in India to install optical sorter at its mines to beneficiate the limestone, because what we believe is that evaluation of the raw materials is important, as all of us know, because we being civil engineers using concrete, we also know the importance of evaluating the input materials, whatever is being used for concrete. And so X-ray fluorescence analyzer at mines is installed to determine the parameters of limestone, which is very important, because unless you do not know the quality of raw materials that is going into the manufacture of cement, how do we make a good quality cement? So that to fulfill that, we have installed all this latest technology, and these are some of the initiatives that we have been taking. Of course, it goes without saying that an integrated ERP system is required to integrate data at all levels of operations, so that we have got, because as all of us are aware, that Ramco is also having, Ramco Group is having Ramco Systems under its umbrella, and Ramco Systems has also been doing a great job as well as ERP is concerned, and so we have been able to do that. Now, to customize the various products based on the application, we have brought a number of brands. 12 brands of cements are there. So what we do is that, as all of you would be aware, we do not recommend a particular type of cement. What we always suggest is that please find out the type of concrete that you're using and the application, where exactly you are going to use, and based on that, go in for the particular type of cement. So, say for example, if there is an RMC unit and if they're able to procure blending material, then they can go in for ordinary Portland cement. It can be either 4353 or infra 43, infra 53. The idea of having infra is that it is giving a higher slump retention. So if an RMC unit or a captive batching plant has the infrastructure to check the quality of blending materials, then they can go in for such kind of cement. And those who are making precast items can go in for Ramco Superfast cement, which is specifically meant for precast application with a high rate of gain of strength. Then, of course, the Portland Pozzolan cement, Ramco Super Grade, Super Crete, Super Fine, and Super Plus are the brands. Portland Slag Cement, again Super Steel and Samudra, and Ramco Super Coast is sulfate resistant Portland cement, which is meant for applications where there is a high quantity of sulfates in soil. So these are some of the brands of cements that are available. And apart from this, we have the dry mix range of products ranging from tile fix, block fix, plastering compound, tile grout. So these are the dry mix range of products which is manufactured from our dry mix plant at Sriperumbudur in Chennai, because we thought that dry mix products, which is meant for non-structural application, needs to have a different set of parameters, which is different from cement itself. So recently we had launched about a year back Ramco Super Crete cement, which is cement which gives a high performance concrete, and the benefits, as of all of you would be aware, those who have used it, especially for individual house building sites where there has been concreting application, we have taken the feedback, and many of them wanted a high rate of gain of strength even in Portland Pozzolan cement, and durability also had to be there. So we have combined both the parameters of durability as well as compressive strength in one cement itself. That is, we have tried to reduce the heat of hydration in the cement. Of course, it doesn't mean that you should not do curing. Curing is required because there is no cement or concrete which goes without curing. So curing is required. and of course you get a high workability. So Ramco Supercrete gives you all these three important parameters: the strength, the durability, as well as high workability. And we have the Ramco Research Development Center at Chennai, which does works in various testing of blending materials, cement, as well as testing of concrete, doing concrete mix design with various kinds of chemical admixtures, and the material that is available locally, like say for example sand or aggregates, and based on that we do the concrete mix design. And we have been doing this for a number of projects over the years, and due to this we have been able to understand the ground reality, that concreting requirements of various professionals. Of course, durability happens to be one of the most important parameters, so we have installed equipment for checking the durability of concrete. One such equipment, as all of us know, is the RCPT test as per ASTM standards. Based on the amount of charge that is passing through the concrete specimen, you can evaluate the durability of concrete. If the amount of charge that is passing is more, that means the durability is less. Anything less than 2000 coulomb is considered to be acceptable. Of course, we have the water permeability test as per DIN standards, which again is being used by some of the major project customers in evaluating the penetration of water. So based on the pressure of water, it can be either 5 bar, and based on that we can check the penetration of water, which gives an indication of durability of concrete. So our concept has always been the right product for right application, based on the right application of concrete, the right type of cement. And we have always taken, as I was telling initially, as well as the leadership in technology, energy efficiency, and utilization of blending materials. And we were fortunate enough to have customers, major project customers, who have used our cement for various kind of concreting applications, like Larsen & Toubro, ITD Cementation, and various institutions who have approved our cement for various projects. So these are some of the interactions that we have got, and some of the projects that we have been associated with. Now, today is the 94th webinar. It has been nice to see that there were many professionals who participated and who also shared their valuable information with the construction professionals across the country. So taking that further, today we have Professor Dr. Anjan Dutta from IIT Guwahati, who would be speaking on enhancement of seismic performance of civil structures, because this particular subject has been of particular interest. There were many speakers who had spoken about this in the earlier webinars, but then, as all of us know, that we have not been giving much importance to this, because we have been taken for granted, because whether it is zone 1, zone 2, zone 3, zone 4, it doesn't happen, or it comes in once in a lifetime, or may not happen at all. So that is a kind of assumption that many of them make. But this has to be given much importance. So Professor Anjan Dutta, who has been working at IIT Guwahati for the last 21 years, he was head civil engineering department from 2006 to 2009, and Dean Institute Works 2009 to 2014. He has published more than 100 research papers in journals and conferences. He has guided several PhD students and is a member of many committees. His area of research work are retrofitting of structures, seismic control, identification of damage in civil structures, etc. He is involved in large number of consultancy projects of national importance. So we are very fortunate to have him, and he would be sharing his experiences with us. I'm sure that speakers who joined us from IITs. We had speakers from IIT Kanpur, IIT Kharagpur, IIT Madras, IIT Bhubaneswar, and of course practicing professionals who have shared their experiences. Now let us listen to Professor Anjan Dutta about his experiences in this particular topic. Over to you, sir, and welcome to this webinar. Thank you so much.
Thank you. Okay. Good morning, everybody. The title of my presentation is Enhancement of Seismic Performance of Civil Structures. Some of the recent activities which we have been carrying out at Structuring Laboratory at IIT Guwahati. The first question that arises to everybody's mind, that why enhancement of seismic performance are needed. Now, there could be two broad reasons. One is, the structures may undergo loss of strength and stiffness with time due to environmental factors. Maybe it is subject to some event like earthquake, or due to age, or the structure which you have designed is now maybe based on some older codal, and the codal provisions have become more stringent now. So your structures may need further enhancement. Now, when you do enhancement, you can actually, you should be looking at it from two directions. One is at the element level. You're looking at the enhancement of seismic at element level. Essentially, the procedure now is you
Sir,
introduce
sorry to
something
interrupt
called,
you. Are you sharing the PowerPoint presentation, sir?
yeah.
But we are not able to see that. You'll have to use the third icon, the share
Okay,
screen.
okay.
You'll have to click on that.
Okay, so far you have not seen anything, right?
Yeah.
Oh, I'm so sorry.
The third icon, yeah, which you have done earlier, no? Same procedure.
Share. Yeah. I thought it is already there. Okay.
Now it's there. Now we are able to see. Earlier you were only able to see. We were not able to see. Now we are able to see.
Okay. I'm so sorry.
It's okay.
Right. So now you can see, right?
It's getting loaded.
No, I think you'll have to stop sharing again, sir. It's not loaded properly. Can we try doing it again? The first button says stop sharing. Okay. We can see your screen now. The desktop.
Where is the?
I see Ramco on the rightmost side on the desktop. Is that the one?
Oh, yeah.
Yeah. The
Yes,
floor is
now
yours.
it is. Yeah, now it's okay, sir.
Yeah.
Thank you.
Is this fine? Yeah.
Yes, it is okay.
Okay. So we are talking about why enhancement is needed, and enhancement, as I said, it could be due to loss of strength and stiffness of a structural element due to environmental factors, which could be maybe the structure is subject to some event like earthquake, or due to aging, or it may be because of the more stringent codal requirement based on, compared to what you have designed for. Now, when you want to carry out enhancement, it can be done actually at two levels. One is element level, other one is at the global level. Now, when you're doing at element level, now which element? So now we have a far more advanced technique like system identification strategies. What we do here, we collect vibration signature from a structure, and we can identify, for example, I have multi-story building, and using acceleration signature from the structure, I can actually find out which floor is having weakness. And then I can go to that particular floor and carry out a detailed non-destructive techniques using maybe rebound hammer, ultrasonic pulse velocity meter, and so on and so forth. And then you identify specific element which needs to be strengthened. Or you may have to have what is called global enhancement requirement. For example, the structure in an overall sense may be weaker for carrying the lateral. So you can carry out one of the techniques could be push analysis, and you find out what is the overall weakness, and then to that extent you carry out the enhancement, and which can be done maybe using a shear wall or some other framing system. Now, one of the if you look at the building structures, one of the major areas of concern is the beam column joint. You will find numerous RC buildings. They actually shown some damage near beam column joint after a severe earthquake. And but again, out of those damages, you will find that most of the damages are confined to outer beam column joint. The reason being, if you look at an outer joint, you'll have the confinement is only from two sides. So obviously it is exposed on two sides. So they are comparatively more vulnerable than the inner beam column joints. So keeping that in mind, what we have done, we have taken some experimental exercise in our laboratory, and we have taken three types of specimen. One is beam weakened fracture, which is what it should be, because we appreciate that all the failure mode should be in fracture, because this is the most vulnerable mode. And then we have taken another case, which is beam weakened shear, maybe the shear reinforcement provided is not adequate, and then column weakened shear. Again, the lateral reinforcement provided in column are not sufficient. We have taken an external frame, and we have taken out one free body of that beam column joint, and carried out experiment now. So let's see what we have done. So this is the arrangement for the testing. This is a beam, and beam is subjected to, we have actually fantastic is at IIT Guwahati, and so I'll show you the part of the laboratory a little later. So this is your column, and this is the beam. So beam is subject to this kind of fluctuating load, simulated through this kind of loading, and we are trying to simulate the effect of earthquake. It's not actually exactly earthquake loading, but then we are providing the loading protocol is with different frequencies and for different duration. So thereby we can actually find out what is the kind of degradation which is happening, what is the ductility and issues like that. This is a typical picture of how we have carried out testing. This is a column subjected to vertical load, which is simulating the gravity loading. Then this is the beam. Beam is subjected to, this is actuated, and this is a dynamic actuator. We can play with the frequency content of the displacement. So this is the beam. Beam is subjected to a fluctuating load. Fluctuating here, the load is actually displacement. So we have three cases, as I said. We have weak in flexure. So this is my beam. This is my beam. So beam which was weak in flexure, now we have retrofitted using FRP, fiber reinforced polymer. These are all carbon fiber. So you have one layer of carbon fiber here, another layer of carbon, and we have put some strip around it so that their possibility of delamination will be reduced. Now, every time you design a beam or column for retrofitting, you have to also ensure that column is made stronger than your beam or particular beam, because any failure in beam will be local. So this is what is the eventual desirable mode of failure. So we also look at what is the requirement in the column, and then put some additional enhancement in column. And then we have tested it. Now, when you have tested your beam weak in flexure, you can see that there is a kind of hinge formation, because eventually it's a beam which is acted upon by load at the tip. So the maximum moment, see that there is a hinge kind of formation. And then when we have retrofitted using FRP, you can see that eventually the delamination, finally at the time of failure, the delamination is also taking place here. Next specimen is your beam weak in shear, and you can see that now the shear reinforcements are increased. You have more strips to make it to get rid of the weakness in shear, because shear mode of failure is actually highly unwelcome, because it's a very brittle mode of failure. Always, if at all a structure fails, it should be in the flexural mode. So we have introduced the shear reinforcement in the form of stirrups, which is using again the FP, and then again simultaneously have looked at the joint region also. And this is the kind of picture which you see after the failure. Again, you can see that the failure is because your shear failure, if you compare with the flexural failure, you'll find that this is far more, is nature. And even eventually, when the retrofitted specimen was tested, the failure was also in the similar region. Then we have the specimen which is column which is weak in shear, and now we have, you can see that the column has been strengthened using shear reinforcement, and these are the failure mode for the control specimen. You can see that the control specimen after the failure, a lot of failures are actually taking place in the column, not so much in the beam. And then eventually, when we have retrofitted, finally, also it's not very clear here, but fine failures are in the delamination of the strips only. Right. So we have two sets of specimen. One is wherein we have control specimen, I call it, without any retrofitting, and then we have another set of specimen which is retrofitted using fiber reinforced polymer. Now the control specimen which you have, that we have further rehabilitated. Now this is something similar to your actual scenario in the field, wherein your structure is subject to some kind of some event, and some elements are damaged. So you may have to do the rehabilitation, and generally rehabilitation is done using epoxy injection and some other constituent materials. We'll just quickly go through what we have. So you use microconcrete as a replacement of material, and then you use concrete bonding agent so that bonding between the old and newer concrete is made. You use epoxy putty so that all the cracks are sealed, and then finally we use epoxy injection under high pressure so that all the cracks inside the specimen fill up. So you use a pressure for epoxy injection. You have to use also injection packer so that these are actually fitted. We'll show you some of the pictures. These are fitted into the specimen, and through these packers, epoxy will be injected inside the cracks, inside the specimen through the cracks. So this is what we have done. First, you remove the spoiled concrete from the damaged region, and then use some concrete bonding agent so that there is a good connection between the older concrete and the newer concrete. And then you patch up using high strength polymer modified concrete, and then you drill some holes in the damaged zone, and you insert packers, and then you superficially seal all the visible cracks, and then finally you inject epoxy through the crack zone. And after this, so earlier we have tested all the retrofitted specimen. Now we have tested again all the rehabilitated specimen. So we have all the pictures for original control specimen, retrofitted specimen, and rehabilitated specimen, and they have all now failed in the desired mode. And finally, you see some of these plots, load versus displacement curve, and you see retrofitted specimen is having more capacity than the original specimen, that is the control specimen. And rehabilitated specimens are more or less similar to your original specimen. This is what is the target. In fact, sometimes you find the rehabilitated specimens are better than epoxy is having very high strength. And you also look at how the stiffness is actually changing as you go on increasing the displacement level. So with higher and higher drift, more and more damage will come in. So there will be degradation in stiffness, and this is what you can look at. And one more important thing which we look at the plot of energy dissipation, because this is what is the measure of your seismic power, very important requirement for ductility. So you can see that your original specimen, if this is the cumulative energy, your retrofitted specimen is having higher energy level. That means it can now dissipate more energy than the control specimen. And similarly, your all rehabilitated specimen, when you look at, they are more or less similar to the original specimen. So thereby, your rehabilitated specimens are as good as, and mind you, the damaged specimens which we have tested initially before the rehabilitation, they were tested to a level load level so that the degradation in load carrying capacity was as high as 40 to 45%. Now you imagine a structural element which has been degraded to 45%. Now we have rehabilitated them using epoxy injection, and you can see that the capacity is back to the original capacity. So it is as good as the original capacity. So there, to carry out rehabilitation, even for a damaged specimen which is as degraded as to the extent of 35 to 45 to 40 to 45% capacity, it can be brought back to the original load carrying capacity. So that's a very encouraging sign actually. Now, so this is what we have done. Local level, we have identified which all elements are having, as I said earlier, for actual structure, you can have a combination of system identification technique and detailed non-destructive technique, and you can find out needs strengthening or rehabilitation. Next, we'll talk about global retrofitting. Now, when I say global retrofitting, that means that it is not just one element or two elements here and there. The structure as a whole is having some deficiencies. For example, if you look at this multi-street building, this is one important structure which we have done here in Guwahati. So if you look at this multi-street building, and the ground floor was fully, dedicated for parking. So it is possibly having a software effect. So we have numerically and carried out pushover analysis, and from the pushover analysis, we have realized that there is huge amount of weakness in the lateral direction, so it needs to be strengthened. So you see, this is a parking area. So parking area, without disturbing the parking area much, we have to find out a ways and what could be the possible means for strengthening it. So this is what we have introduced some shear wall in some selected part on this side, and because parking has to be from this, and this is stair, of course. So these entries are undisturbed, so the parking can still be there. And we have introduced some shear wall, and again, not for the full part. The performance, and I found we have selected performance prevention, even collapse prevention. So for a building like this, collapse prevention is good enough. So we have the performance level of collapse prevention. We have found out what is the requirement, and based on this requirement, we have decided that a shear wall of this much of height will suffice our requirement. Right. So next important thing which we have done is we have tried to see how we can improve the seismic performance of elements using some improved concrete. So in concrete now we have used what is called hybrid fiber. Now what is hybrid fiber? Hybrid fiber is a combination of more than two types of fiber. So in our case, we have used a combination of steel fiber and polypropylene. Now there are numerous studies which are already there at the global level, but it was important for us to carry out these studies because we have to use the Indian made fibers. So we have used Rectron and we have used Bajaj Plast because we have to know these are some of the typical, because it should be non-reactive to the concrete also. And we have used steel fibers. Now steel fibers are having some hooked end at the end. And these are the typical tensile strength for steel fibers and polypropylene. Ratios are quite different. When you look at the aspect ratio of steel fiber, this is 65, and this is so we call the steel fiber as microfiber and the polypropylene as macrofiber. So we have macrofibers. Now what happens when they are mixed in concrete? And a concrete specimen is loaded. So once it is loaded, eventually it starts developing crack. So initially there will be small cracks, or we call micro cracks. So whenever there are micro cracks, the microfibers will try to play a role there. So it will try to immediately arrest those micro cracks, because eventually those micro cracks get coalesced and develop a macro crack, and finally it leads to a major crack and collapse. So in this case, your microfibers will immediately try to arrest the micro cracks, and then once you go beyond a particular load level, micro cracks perhaps will not be further arrested, but then your macro fibers will come in, and it will try to prevent more cracks. In process, we have seen that concrete. We'll see subsequently concrete specimen, for example, a beam. Once you load, you know that below neutral axis there is tension, and then above neutral axis you have compression, and the tension zone is not participating in the load carrying. Now, if you maintain this compression zone for long, you are done, because the load carrying capacity obviously will be a large part of the concrete will be in compression, and they will all participate in load carrying capacity, and thereby the share of load on steel will be lesser, and you'll see that the strain in steel will be much lesser compared to your specimen without fiber for much longer duration, and eventually the load carrying capacity will be larger. So to begin with, we have taken at the test at the prism level, and if you look at the failure pattern of a prism without any fiber, it is brittle. Obviously, it is brittle, no reinforcement, it is highly brittle. And now when you use those fibers, hybrid fibers, you can see that even with much higher load, this is the 29.8 versus 18.4, and modulus of rupture is also obviously much increased. And so this is what is the motivation. You can see that the ductile behavior of the specimen, the concrete will be much higher now, which is otherwise very brittle without any reinforcement, and that is why we use reinforcement. But then with reinforcement, and also we understand that particularly in the beam column joint, where there is a congestion of reinforcement, can we also reduce the reinforcement, because otherwise the concreting is also a problematic area. So this is another we explored that using those fibers, can we also reduce the congestion in concrete? So once we have got some success at the element level, we have taken a bridge. This is a prototype bridge in Tripura, and it was designed in a seismic zone. This is the dimension of the prototype. So in the laboratory, we have tested a 1/5 scale of the this specimen, column specimen, and this is how we apply the horizontal displacement load, and this is the vertical load, which will simulate the gravity load. So this is how you. This is one of the actuators, and this is another actuator for horizontal load. We'll go to the next picture, which will make it very clear. This is a view from the top, and you can see we have, as I said, we have a fantastic laboratory. This is your strong floor, this is strong wall, and the specimen is resting on the strong floor. And on one of the strong wall, you have the horizontal actuator, which is fixed, which will provide the displacement in the horizontal direction. And we have a loading frame. From the loading frame, the vertical actuator, with which is the gravity load. And we have LVDT here. It can monitor all the displacement, and entire specimens are a lot of strain gauges are fitted inside the reinforcement, so we can actually monitor what is happening to the strain and all. So this is what it is. This is the skeleton of the, and you can see that strain gauges are fitted in the longitudinal reinforcement as well as in the transverse reinforcement. And I'm a lot of figures are there because these are all part of PhD programs. So obviously you can expect a lot of results. I'm showing some of the cell. So after the damage, you can see one such typical specimen with and without fiber. This is without fiber, and this is with fiber. One which is without fiber, the reinforcement, everything is exposed, and this is both at the same reinforcement displacement level, 100 millimeter. And you can see also the concrete crushing was happening at 40 millimeter for specimen without fiber, and same thing was happening at 60 millimeter. And only two reinforcement got ruptured eventually for specimen with fiber, and whereas one more additional reinforcement got ruptured in specimen without fiber. And you can also see what is for specimen without fiber, the strain is as high as close to 6,000, and this is close to 6,000. Now, these specimens were, we could enhance the ductile behavior of the specimen and also the load carrying capacity of the specimen hybrid fibers. Next, what we are planning to use memory alloy. Now, this is a very recent trend and a very new trend in civil engineering. Shape memory alloys are used by dentists, used by mechanical industry, but it is still not application in civil industry because the typical memory alloy which you see in industry are NITI, and they are very expensive. Now, when you look at civil industry, the requirements are massive. So you cannot really use those kind of expensive shape memory alloys. So we are looking for cheaper shape memory alloy, and we have found one shape memory alloy which is iron-based, FeSMA, and we eventually into the details of this SMA, some of the basic principles of SMA. We have a SMA strip, and we have pre-strain, and it taken to this level, right? Now, when we have pre-strain, and there is some level of, generally we do it up to 2 to 3% of pre-straining, and then we fix it to, let's say, concrete specimen by anchoring, by using some bolts, right? And after this, we do some thermal activation now. Now, once you do, now please understand that this is shape memory. So it remembers its original. Now, original shape was this one, and we have pre-strained at this level. Now, when you do this thermal activation, it tries to go back to this shape, original shape. Now, what will happen when you try to go back to this original shape? It will, in the process, it will introduce compression in the concrete. Now, what is the benefit? Now, if I use this pre-strained, if I encode this pre-strained element shape memory element in the tension zone specimen, and then I carry out this thermal activation, it will introduce a compressive force. So it will be something similar to your pre-stressing. And what we actually do in pre-stressing, similar scenario will be prevailing there. So in the process, we can nullify the tension which will eventually develop in the concrete specimen when they're loaded. And this is one scenario. Another scenario could be if I wrap it around. If I use this kind of thermal activation, it will try to have more and more confinement on the concrete. Now, if it is having more and more confinement on the concrete, obviously the ductile behavior. So these are two such properties which are trying to exploit from the SMA. So this is SMA. Now, let's go back to the Fe-based SMA. The Fe-based SMA composition is Fe17, Mn, manganese 5, silicon 10, chromium 4, and nickel 1. So you can find the large share of iron is there. So thereby the cost has gone down significantly compared to what is generally available as NITI. And this we have got it from, we have, fortunately, we could have some collaboration with Swiss Federal Laboratory of for Materials Science and Technology. This is called EMPA, and they have supplied us this strip. And right now we are in the process of using this in our laboratory. And we have already carried out some numerical studies. This is what I'll show you now. So this is how we'll do. Say suppose this is at the cylinder level, we can vary the spacing, and we'll do some thermal activation. So it will have more and more confinement effect on the specimen. And eventually this is what we are trying to see exploit, so because this will give us more and more ductility into the specimen. Right. So the brief specimen which we have done tested earlier using fiber reinforced polymer, hybrid fiber concrete. Now those damaged specimens now we are rehabilitating. So we have done rehabilitation using the standard rehabilitation procedure. We have cleaned all those loose concrete. We have done some patching using micro concrete. Then we have sealed all those using, of course, we have used bonding agent between the old concrete and the newer concrete. And then we have done the patching using micro concrete. And then we have sealed all the visible cracks using sealant. Then we have drilled some holes, used packers, and then carried out injection using epoxy injection pump. And specimen is rehabilitated. Now this rehabilitated specimen will be now, different strategies we'll try to use now. Some specimen one will be your control specimen, one will be only using hoop reinforcement, one will use what we call as near surface mounting. We'll only mount on the surface strips. And then if we use thermal activation, they will introduce, because we are using loading like this, reversible loading. Because we have seen, this is what we have seen, the loading protocol to simulate the dynamic environment. So it will generate the tension phase on this side as well as on this side. And we are using near surface mounting. And after thermal activation, it will introduce tension in this zone, compression in this zone, so that whenever you have tension because of loading, it will try to nullify those tension. And another one which are, this is called embedded. One is near surface mounting, other one is M1, and we will try to see what are the advantage and disadvantage of each one of these. And we have already carried out numerical simulation for each one of these. And based on the observation from numerical simulation, we are going for the experiment. So these are some of the results from numerical simulation, and you can see that there are certain enhancement in the load carrying capacity as well as the rate. See, if it is falling like this, obviously they are degrading. And it is much flatter, so obviously the degradation is much lesser. And so your pre-compression as well as confinement effect which you are getting because of the hoop, they are all coming to our advantage. Right. So this is what we have done so far at the element level and also the global level. And we are trying to enhance the capacity, seismic capacity, either in terms of load carrying capacity or energy dissipation. So this is one approach. So essentially, there are two approaches. One is wherein you increase the carrying capacity of the specimen so that the structure will be safer. Other one is you reduce the demand on the structure. So our next set of presentation where we will try to see that can we reduce the demand on the structure will be safer. So one of the procedures as to by which you can reduction in the demand is using seismic isolation strategy. Now, what is this one? Let's look at a little bit. Now, conventionally, which is our conventional structure, they cannot be realistically designed to remain elastic in large seismic events because it's not just possible. So what we do, we try to find out fewer areas where fewer regions where you can develop high design for common practice should design them so that they experience damage in the controlled manner and can undergo large inelastic displacement at those locations. Now, if you look at the entire gamut of, there are passive control system and active control system. The one which we are talking about, isolation system, is a typically passive control system wherein you don't require any external energy, but you have also active control, semi-active control, and hybrid control, wherein you require active control. Of course, you require large amount of energy. It is very difficult to ensure because when you have earthquake, the power system itself may go off. So, semi-control active system are popular, but right now in this presentation, we'll consider a base isolation system wherein we don't require any external energy to be supplied. So the objective of seismic isolation system is to decouple the building structure from the damaging components of the earthquake input motion, superstructure from absorbing the earthquake energy. So if you can do that, our structure will be safer. So what do? The entire superstructure will be now supported on some discrete location, some discrete isolators, whose dynamic characteristics are to be so chosen that overall we'll see that the structure is inviting lesser force. So this is what happens. If you have structure, conventional structure, you will have interstory drift, and because of the interstory drift, the structure, the load carrying element will experience a lot of forces, and also you'll have a lot of vibration, flow level. But if you have a seismic isolated building, you can see the major displacement will be happening at the isolation level, and there will be hardly any interstory drift. There will be hardly any movement. So what will happen if you do not have any interstory drift? The structural elements, the load carrying elements, will be unstressed, under stress. So thereby you can design them much lighter, and because your major energy is getting dissipated here, and entire structure is actually experiencing a reasonably kind of motion. So this is what you'll see now. Of course, your base isolation system, before you employ, you have to see that they are going to be suitable for following condition. The structure type with sufficiently high column load. Otherwise, if the column load is not high, the isolation system which will develop, they themselves become slender. And if they are slender, they become little unstable. And the site permits displacement because the isolators will undergo displacement. So your site has to permit that kind of displacement to happen. And of course, you have to see, because there are always earthquake load can come once in a while. So you have to ensure that the structure is not always oscillating under the wind load. So this is what you can ensure. This is a typical response spectrum which we use for design. And if this high, the period of the structure will be for fixed base, typical example you are talking about. And so in the process, it will invite so much of seismic force or response will be at this level. Whereas if I have a base isolated structure, the time period will be lengthened. So if the time period is lengthened, it goes somewhere here, and thereby the response or the seismic force which the structure will eventually invite will be much, much lesser. So thereby the structure which will be designing for much lesser force. These are some of the typical isolation system which you can see commercially. Now, IIT Guwahati is fortunate to have a base isolated building long back. I mean, it's about 10 years now. It was sponsored by BRNS, Board of Research for Nuclear Science. So you can see we have a conventional building here, and you have a base isolated building here. These are my base isolation. And those isolators, they came from Robinson, came from New Zealand. And entire building is instrumented using these meters. And if you see there are some of the records which you have, because fortunately a lot of earthquake. And so you can see that if this is the ground motion, having the peak value of 0.023, it could reduce to as low as 0.001 at the roof level. So there's a huge reduction in the acceleration response. And this is we have some records at 10/9/2006, 6/11/2006, and many others subsequently also. And you can see the percentage reduction, quite good amount of percentage reduction you could see. But what is using this while installing the isolators in this building, that these isolators are actually laminated high rubber bearing isolators, and you have a top steel plate and bottom steel plate. So they are very heavy, and there are also in between steel plates, and they are now these are extremely labor intensive because they're very heavy. But this is not so accessible. So thereby we thought that can something else be done? An isolator which reinforced elastomeric isolator, wherein the steel layers, because in laminated rubber bearing, you have rubber layers and steel layers, rubber layers and steel layers. And the top also, top and bottom, you have thick steel plates. Now, the one which I'm talking about now, fiber reinforced elastomeric isolators, they are the steel layers are now replaced by fiber reinforced plastic, using the carbon fibers, because we know the elastic modulus are very high for carbon fibers, so they're comparable. And but when you look at the weight is many times lesser than steel. So, and another important advantage which you get, that when you want to connect, use steel plates for laminated rubber bearing, you have to use sandblasting, you have to use acid cleaning, and all these are now not required when I'm using FRP, because I can use FRP and heat it a little bit, and then put it in a chamber where I can control the temperature to say about 40 to 50 degree, and go on putting one layer of FRP and then one layer of elastomer, and then subsequent layers one after another, and eventually can develop a isolator like this. And these isolators are very, very light. You can make a large structure and you can cut them into pieces, and this is what you can do. So it's very, very easy to manufacture. And then another major advantage, I don't any top and bottom plate. I can just put them between structures. So this is what it is. You have one layer of fiber and one layer of elastomer, and then you can develop a multiple. To begin with, we have made a model structure. We have tried at a smaller scale. So our isolator size is 100 by 100, and the thickness is again some 104 millimeter. And these are the fiber layer thickness and elastomer layer thickness. To begin with, we've gone for numerical testing. We have done a detailed numerical analysis. We have carried out finite element analysis. Now, finite element analysis for this kind of problem is a little tricky because this is involving elastomer. So you have to use appropriate kind of element. And so we have done the simulation in ANSYS, and we have used this kind of loading protocol. Slowly, we have increased the displacement range. And this is what you can see now. So in the numerical simulation, I can have anything. I have used one which is connected to the superstructure and substructure, and I have used another one which is unconnected. The one which is not connected, you can see a what we call is a rollover deformation. Now, what is happening? If the rollover deformation is like this, it is actually in contact with only this flat surface. So thereby, the actual transmissibility of the vibration from the substructure to the superstructure, it gets substantially reduced. And one more important thing which is happening, look at the one which is fully connected to the substructure and superstructure. This red zone is actually a tension zone. So tension zone, when you compare with this with the unconnected one, tension zone is much lesser. So what will happen in the process? The amount of tension developed in even the tension value. So there's a possibility of delamination, because tension is the one which is responsible for delamination of FRP from the elastomer layer. So tension is much lesser. So they are much stable compared to the one which is connected. Right? And then we have carried out a detailed numerical study with different directions of loading. loading which is parallel to the direction fiber, normal to the direction fiber, 45 degree to the direction fiber, and we have found out the corresponding load displacement curve for both bonded and unbonded type. And when I say bonded, that means they are connected to the superstructure and substructure. Unbonded, it is undergo a rollover deformation like this. And you can see for the unbonded, you have the initial stiffness, and then there is some reduction in the stiffness, but then it is nowhere it is negative stiffness. So there, if this stiffness is reduced, so what will happen? The overall stiffness of the structural system will go down. So thereby my time period of the system will increase, and in the process, in the response spectrum, in the time period will be lessened. Time period will be increased because the stiffness is lessened. Time period is increased, and in the process, the seismic force invited to the structure will be less. So from all these numerical exercise, we have found out what is the stiffness at different displacement level, and you can see that as you go on increasing the displacement, they become more and more effective. Why they are more and more effective? Because lesser and lesser the original stiffness, lesser and lesser will be the stiffness of the overall system, and higher will be the time period, and it will invite lesser and lesser seismic force. And also the damping force, you can see it is as high as 14.3%. We have carried out detailed experimental investigation, and for this kind of isolator to find out those characteristics, because numerically when you do, eventually after you have manufactured, and this is a requirement for base isolated building, that every isolator needs to be tested. So we have tested them, and you can see now this is what we have got in the numerical simulation, that there is a step rollover deformation, and you can see the rollover deformation here also. And this is actually connected to the not connected, they are only in contact with the substructure and superstructure. Load displacement or numerical, they are more or less very good match, you can see. After having got this success, we have a shake table, uniaxial shake table of 5-ton payload. A pure masonry building, no reinforcement, pure masonry building, and this masonry building is now supported on those isolators, right? And then we have used some standard excitation of different scale. These are some of the excitation: Koina excitation, far-field excitation, L-center excitation, Mexico excitation. Each of these excitation is from different source and having different characteristics. So we have used excitations of different characteristics, so that we can see that all the ranges. And this is what you can see, another picture when they are tested. This is the rollover deformation. The rollover deformation you can see. This is fully the full PGA is applied, full excitation range. And this is what you see. This is the ground acceleration you can see, and this is the floor acceleration. So there's a huge reduction in the acceleration level. So if the acceleration level is reduced, obviously all the member forces, everything will subsequently reduce. You will also see what is happening to the displacement, and you can see that the acceleration for different floor level, they are more or less similar. So that means all the floors are experiencing similar kind of acceleration, and there's a huge difference of acceleration between the input acceleration and the floor acceleration. And you see what is the displacement. The displacement at different floor levels are more or less similar, which indicates the structure is undergoing a rigid body deformation. So all your structural elements are hardly experiencing any displacement. And this is what you can see. These are percentage reduction, and no, these are the acceleration different level. You can see that acceleration at base and floor and roof, they are more or less similar, whereas at shake table level, which is the input acceleration, they're much higher. Similarly, when you look at the displacement at different level, they are more or less similar. So that means they are undergoing a rigid body kind of. Having sparked by this success, we have gone for a prototype building. Fortunately, we got an offer of prototype building from Arunachal Pradesh government, and we have made a building for them in Tawang, supported on our isolator system. So we have made a prototype. These prototype isolators are of this size, 250 by 250 by 100 and 310 by 300 by 10 by 100. We have tested them in a as detailed manner as possible in the laboratory level using this kind of, and see, you can see this kind of rollover deformation. These are some of the static loop, and we have loaded them from different direction, 0 degree, because you do not know earthquake will come from which direction. So you have to actually see their performance by loading them from different directions. So we have loaded them from all possible directions, and you can see the corresponding rollover deformation from different direction of loading. And these are the, again, static loop when you compare the numerical one with the experimental one, and very good match you can see. These are the, of course, numerically we cannot rather go, experimentally we cannot really go beyond a level because there will be safety of the setup. But this 80 millimeter which you have tested, that is large enough to introduce large nonlinearity into the system, and which is what we have compared with the numerical simulation. They are having a very good match, and with this we have gone further in numerical simulation. And this is what you see. If this is a bonded kind, which is a typical isolator type, what you see in a Piranesi building, the load deformation curve is something like this. Well, our kind of isolator FREI, unbonded, some time you see there's a huge reduction in the stiffness. So thereby the time period of the entire system will be hugely lengthened, and thereby we can invite much less and lesser seismic force into the structure system. Again, we have carried out numerical simulation, and you can see the tension zone much lesser here. But before you go for you should also check the stability, and you can see we have carried out we have played with the displacement level 0.89 TR means total thickness of the rubble layer, 1.5 because code says because we don't have any Indian code so we follow ASC American code, and they said that you have to test it up to 150 1.5 TR. All these points are much higher, so will tell you this is my design load line and this is my stability. It is highly stable under the vertical load, no issue. Vertical load and horizontal load combination, in which we have made in Tawang, the isolation system, and isolation system, the final configuration you can see some, and we have maintained the local architecture. These are all masonry building. Here, and we have also carried out, as this is what you can see in the zoom view. We have also carried out numerical simulations of the entire building. This is the model of this building numerically, and with isolation carried out fragility analysis for different damage level, and you can see the of exceeding a particular damage level is much lesser for base building compared to feature. And this is what has been the motivation. And fortunately, now we are going to construct another 2 buildings in Arunachal, 1 building in Guwahati. Hopefully, many more buildings will come up. So these are some of the people who were involved. My colleague from IIT Guwahati, Professor Eskader, and these are all my students, either master students or PhD students, and my supporting staff. And this is industry partner from Metco, who have helped us in developing this, manufacturing this isolator. Thank you.
So, thank you, sir. It was
yeah.
So it was a very interesting presentation on this one. There is a question. Can we take the questions?
Yeah, please.
This by Mr. Arun Kunal. He has asked, will you please highlight the performance of SMA in elevated temperature? Will it expand and lead to a brittle failure?
This is the SMA. Typically, when you look at an iron, when you heat, it expands, and then we put it around the cartwheel and when contract. But for shape memory alloy, it is just different. It's just opposite. We have pre-strained them, but since it is a smart material, it remembers its original shape. Now, when you have pre-strained them, it's in what is called, it undergoes martensitic transformation. So it is in martensitic phase. Now, essentially, SMA is your metallic alloy, and it has austenite phase and martensite phase. Now, when we pre-strain them, it is in martensite phase. Now, then we do the thermal activation using either resistive heating or some heating like that. And then it tries to go back to the austenite phase. Now, in austenite phase, it tries to regain its original shape, and thereby it introduces that pre-compression or confinement. Stable, very stable.
You see if there is a, but has it been practically implemented anywhere else?
As I said, that these are very new to civil industry. We are trying to see that can we, because see, if a particular bridge is damaged, repairing generally will take a lot of time. But if we can introduce this kind of technology, it can be actually the traffic can be brought in much faster. So we are trying to see what best can be done. But these are very new technology coming in. Only if you look at the literature of application of SMA for civil structures, you will find hardly few, very few. A few experimental investigation has been done by that Swiss group. I think we are maybe second, which will start off in the world.
Okay. Yeah, that's nice. So I think a lot of activities are going at structural
yes,
lab
we are
at
very
IIT.
fortunate. We're very.
That's very nice, because the thing is that all civil engineers must be aware of the developments that is taking place in this particular field.
Absolutely.
Thank you so much, sir, for having spared your time with us and spoken about this. And we thank you, and we thank all the professionals who have logged in. And the recorded version of this talk is available on YouTube, and you can always refer to those. And there were some requests from the participants as to whether we can see the talk again. Yes, you can see the talk again whenever you are free, and you can again go through that. And if there is any queries, please write to us, which we will email to the speaker, and based on his time, he would revert back. So that's very nice, sir. And tomorrow again at 11 o'clock, we have one more talk by Dr. Subhash Yargal of NIT Surathkal, and he would be talking about sustainable concrete construction. So this series of webinars will be continuing, and I'm sure that professionals who have been joining, please feel free to share your comments and share your feedback, so that it would also help us to look at a different way of the format, or
so there should be a good bridge between academia and industry, because whatever we are doing, that should get eventually translated to industry. So that's the.
Yes, that's very true. I think otherwise research papers will be in.
No. We want that finally should get implemented. Yes.
Yeah. So I think, as rightly pointed out by you, sir, Professor Anjan Dutta has hit the nail on the thing. And in fact, his point is very well taken. I think what is important is that we need to implement many of these aspects and many of the research thing. And I think this pandemic has taught us to be more innovative. Of course, that is one thing, because we need to be innovative.
Yes.
Exactly. So we need to look at opportunities that is available, because that is the only thing that we can do as of now.
True.
That is within our control. I think all the professionals can further, update their knowledge and try to see how it can be implemented and be creative. So with those few words, let me thank all of you. And I sign off from today's webinar. And once again, thank Professor Anjan Dutta for his time.
Thank you.
And thank you so much. Stay safe, and wishing all the best. So signing off from the. Thank you.